Okay, so now I want to go over molecular orbitals. So when we have molecules, they can have the hybrid orbitals, and they will also have molecular orbitals. So I want to describe what molecular orbitals mean. So the difference between atomic and molecular orbitals is atomic orbitals just describe the distribution of the electron density around a single atom in a molecule. So we can say sometimes the electron density is completely symmetrical, so like an s orbital, or like a p orbital, or we have a situation where we have hybrids like sp, sp2, or sp3. Molecular orbitals instead describe the distribution of electron density around two or more nuclei in a molecule. So we're going to have two different types here, which will be sigma and pi. Okay, so sigma bond is when we have the orbital overlap that's only along the bonding axis between the two atoms in the molecule. So electron density is between the two nuclei along the internuclear axis. So here we have three examples. Here we have diatomic hydrogen, where we have the electron density is between those two hydrogen atoms along the internuclear axis. So we can imagine here we have an axis between the two hydrogen atoms like this. And then we have these two orbitals overlapping each other. Here we have hydrogen and chlorine, hydrogen chloride. Again, we have a sigma bond here. The electron density is just between the hydrogen atom and the chlorine atom. Same thing with diatomic chlorine. We have electron density just between the two chlorine atoms, so along the internuclear axis. So imagine an axis along here. Electron density is just around that. Now this is different from a pi bond. A pi bond is when we have sideways overlap of p orbitals. So we have electron density above and below the internuclear axis. So I'm just showing you this. Here we have the two nuclei in our molecule, and then we have the p orbitals of those two nuclei in overlapping. So we have electron density above and below, and this would be the internuclear axis in the middle here. Okay, so we're going to have pi bonds when we have double and triple bonds in our molecule. So these exist when we have double or triple bonds. Okay, so let's go over some examples. Here we have ethane. Ethane C2H6 only has single bonds in the molecule. So each of these single bonds have electron density between the two bonded atoms. So here between the carbon and hydrogen, carbon, hydrogen, carbon, hydrogen, carbon, carbon, and three other carbon hydrogens. These are all sigma bonds. So this molecule will have sp3 hybrids. These sp3 hybrids are overlapping in the middle here to form sigma bonds. So here we have our sp3 hybrids. Around each carbon. The hydrogen only has S. And along the middle, when those two sp3 hybrids overlap, we have the sigma bond there. We have an sp3 and S overlapping here to have a sigma bond, sigma bond, sigma bond, sigma bond, sigma bond, sigma bond. Okay, so let's compare that to ethene, which has the formula C2H4. So in ethene, we have two carbons in the center. Each of those carbons will have sp2 hybrid orbitals. So these are these light purplish things are sp2 hybrid orbitals. And then each hydrogen has an s orbital. And these blue lobes in the middle here, these are p orbitals on the carbons in the center, and those overlap to form pi bonds. So here we have pi bonds, which represent electron density above and below the plane of our molecule, and we have sigma bonds between the carbons and the hydrogens in the plane of our molecules. So this molecule here has 5 sigma bonds and 1 pi bond, which is that green thing there with the electron density above and below the plane. So anytime we have double or triple bond, we will have pi bonds represented in our molecule. Compare this to Ethyne, which is C2H4. Here the carbons, these purplish things here, these are sp hybrids. And then we have our hydrogens with the s orbitals. So these are overlapping to form sigma bonds. And then for our triple bond here, we have the p orbitals from carbon, 2 sets of p orbitals, which overlap to form the pi bonds. This molecule has 3 sigma bonds, and we have 2 pi bonds. Okay, so now let's compare this to benzene. So remember, benzene has it has resonance. So if you remember, benzene has alternating double and single bonds in the molecule. So we drew it like this. With the hydrogens off of it. So this molecule has actually 3 pi bonds and lots of sigma bonds. So what we see is that when a molecule has 2 or more resonance structures, that we do have that, also we have that pi bond overlap, and that allows electrons to kind of be distributed over the whole molecule between all those carbons. And if you remember, I told you that each of these bonds is kind of like halfway between a double and single bond. So the fact that these p orbitals do overlap explains that delocalized model of the electrons and bonding and helps us to understand resonance. Okay, so the last thing I want to go over is the strength of sigma bonds compared to pi bonds. So sigma bonds are the stronger bond since electron density is between the 2 nuclei along the nuclear axis in the molecule. Pi bonds are weaker. So what we also see is that single bonds are going to be 1 sigma bond. Double bonds will be 1 sigma and 1 pi, and triple bonds will be 1 sigma and 2 pi's. So as far as the bond length, remember the single bond is the longest. The triple bond is the shortest. Because we have 3 different types of interactions here with the triple, this will be the strongest, and the single will be the weakest. So the strength goes from the weakest to the strongest here, and the length goes from the shortest to the longest this way. Okay, so what we're going to do now is we're going to just practice this again with that sheet we were working on the other day. So when you have just single bonds in your molecule, it's only going to have sigma bonds. So this will have 4 sigma bonds. Here we just have 2 sigma bonds. Here, since we have double bonds, we have 2 sigma and we have 2 pi's. Here we have 1 sigma and 2 pi's. Here we would just have 2 sigmas. Here we would have 3 sigmas. Here we have 1, 2, 3, 4, 5 sigmas, and then 1 pi. So each bond in your molecule is going to be a sigma bond. If you have double or triple bonds, those will count as an additional pi bond. Double would be 1 additional pi, triple would be 2 additional pi's. So that's how you figure that out. Okay, so I want you on your homework to try to figure out how many pi and sigma bonds you have in each of your molecules.